Hey everyone, welcome back to the channel of Roller Coaster with Math. Today we are diving deep into vector spaces and the basis, two fundamental concepts in linear algebra. By the end of this video, you will know how to check if vectors are linearly independent, how to find a basis for a vector space, and how to determine the dimension of that space. Let's get started. Let's start with the basics. A vector space is a collection of vectors that can be added together and multiplied by scalars, and it satisfies a set of properties like closure under addition and scalar multiplication. In simple terms, a vector space is just a set of vectors that follows some rules. Addition and scalar multiplication. So, vector spaces a vector space is a collection of vectors that can be added together and multiplied by scalars and it satisfies a set of properties like closure under addition and scalar multiplication. Vector addition, we have, for example, we have vector v and the vector w. Addition is vector v plus vector w, and we can visualize this as vector v and vector w. Then we get a vector v plus w. And for scalar multiplication, we have a scalar times a vector. For example, we have a scalar 2 times the vector v. K in here refers to a scalar. So, if we have vector v, then 2v would be twice of original vector v, then this will be 2v. Now let's jump into a problem. We have two vectors. v1 equals to 1, 2. And v2 equals to 2 and 4. We want to check if these vectors are linearly independent, and if not, we will find a basis for the space spanned by these vectors. Lastly, we will determine the dimension of that space. To check if these vectors are linearly independent, we need to see if there's a non-trivial combination of these vectors that equals the zero vector. In other words, we ask if there exist scalars C1 and C2 such that C1 times V1 plus C2 times V2 equals to 0, 0. So in this case, we will have C1 times 1, 2, which is a vector V1, plus C2 times vector 2, 4 equals to 0, 0. Now let's explain this out. We have C1, 1, 2 plus C2, 2, 4 equals to C1 plus 2C2 and 2C1 plus 4C2 equals to 0, 0. This gives us the system of equations C1 plus 2C2 equals to 0 and 2C1 plus 4C2 equals to 0. Now, if you notice, the second equation is just double the first. So we only need to solve one equation, which is solving C1 plus 2C2 equals to 0. We find that C1 equals to negative 2C2. Now, this is a dependent relationship between C1 and C2, meaning that V1 and V2 are not linearly independent. There's a non-trivial solution, so the vectors are linearly dependent. Vector V1 and V2 linearly dependent. Since V1 and V2 are linearly dependent, we cannot use both as a basis for the vector space. A basis must consist of linearly independent vectors, so we need to find a basis for the vector space spanned by these two vectors. So we need to first we know that a basis must consist of linearly independent vectors. Okay. Since V2 is a multiple of V1, we can just use V1 as a basis for the space. In other words, V1 equals to 1, 2, forms a basis for the space spanned by V1 and V2. Finally, let's talk about the dimension of the space. The dimension of a vector space is simply the number of vectors in a basis for that space. Since we only need one vector to form a basis for this space, the dimension of this vector space is 1. So we need to know the dimension of a vector space is the number of vectors in a basis for that space. And we only need one vector to form a basis for this space. So the dimension of this vector space is 1. That's it. The vector space spanned by V1 and V2 is a one-dimensional space, meaning it's a line in two-dimensional space. So let's recap everything we just learned. We checked if the vectors V1 and V2 are linearly independent and found they are dependent. And we found that V1 alone forms a basis for the space. And the dimension of this space is 1. Alright, if you enjoyed this video, don't forget to like, comment and subscribe. Also, let me know in the comments if you'd like to see more problems on vector spaces or any other topic in linear algebra. Thanks for watching and I'll see you in the next one.